Hey guys, let's check out this conservation of angular momentum example. So you stand on a stool that is free to rotate about a perpendicular axis to itself and through its center. So there's a stool. The stool, let's get a little stool going on here. And this thing can rotate around itself about an axis perpendicular to it through its center. So imagine that the stool is this and it rotates and you're on top of it. Perpendicular makes a 90 degrees, right? So this means that the stool rotates like this with an axis through its center. So just like a normal stool if you are on it. So you stand on the stool and it says that suppose that your combined moment of inertia, U and stool, is 8, and that it is the same whether you have your arms open or pressed around your body. Now, that's not true, obviously, because if you close your arms, remember, moment of inertia is some version of mr squared. If you close your arms, your R is going to drop, which means your I drops, okay? But in this problem, just to make things simpler, we're saying that this change is negligible, okay? So when you close, it's going to stay the same. So initially, so that's not going to happen. Initially, with arms open or closed, your I will be 8. So let me draw this here. U with your arms open, I equals 8. And then U with your arms closed. Over here, something like this, right? Close against your body. Your I will be 8 as well. And then it says here that you stand on the stool with arms wide open, holding one 10-kilogram weight on each hand at a distance of 80 centimeters from the central axis. Now, if you're on top of the stool, you're going to rotate around yourself. So the central axis, imagine, is a line through your body. Okay, so the central axis looks like this. Okay, so what we're actually going to have is I'm going to draw this one more time. We're going to have one last time. You holding weights with your arms wide open. So here are the weights you're holding. They have mass of 10. So the I of the system is not going to be 8. The I of the system is going to be the I of you plus these two weights. Both weights have the same mass. They are the same distance from the axis, which is 0.8 and 0.8 meters. And these guys are 10 kilograms each. Okay, so the moment of inertia of the system is U plus 2 times the moment of inertia of the little masses, because they're going to be the same moments of inertia. Okay, your moment of inertia is 8, but you'd have to calculate this piece here. Okay, so we want to first, and that's what we want to find out first. We want to calculate the system's total moment of inertia about its central axis. So I already have that it's 8 plus 2I. I is the moment of inertia of the little objects. The objects are point masses because they're shapeless. They have negligible size. The moment of inertia of a point mass, remember, is mr squared. So this is going to be 2 mr squared. The mass is 10 and the distance is 0.8. And when you do all of this, you get that the I of the system is 20.8. 20.8 kilograms times meter squared. So this is part A. For part B, it says, suppose a system spins with 60 RPM. We want to calculate the angular momentum that you have. So I calculated I, and now for part B, we want to find what is L. What is L of the system if it has an RPM of 60? Now remember, L is I omega. I just found the I just have to plug in omega. I don't have omega, I have RPM, but I can replace, right? So I can write I, and instead of omega, I'm going to write 2 pi RPM over 60. RPM is 60, so this whole thing just becomes 1. And I end up with L equals 20.8 times 2 pi. And this is going to be 131. Okay, units are kilograms, meters square over seconds. That's L. Very straightforward. Just plug and play. For part C, it says you bring the weights to your chest so that they lie on the axis of rotation. So the weights were out here. The axis of rotation is like an imaginary line through the middle of your body. So you're putting the weights on the axis of rotation like this. Okay? And then it says calculate the system's new moment of inertia. So now what you have is not this picture. Instead, what you have is a situation where your arms are actually closed. So I'm going to draw this one last time. So you have a situation where your arms are closed. So something like this. Okay, that doesn't look awesome, but that's what we're going to roll with. You are holding these weights like this. And remember, if you changed the way your arms are set up, it didn't affect your moment of inertia, but it will affect the moment of inertia of the weights, because the moment of inertia of the weights depend on mr squared, where r is the distance from the axis, and that's changing. I used to have a distance of 0.8 from the axis, and now the distance to the axis is 0. Okay, it's 0. So the new moment of inertia, I system new, or final, I guess, if this one is initial, is going to be IU plus 2I, or 8 plus 2 mr squared. But the r, this is at 10, the mass, the r is becoming a 0, so this whole thing is gone, and the only I you have is your I, which is 8. Okay? That's it for that piece. And then the last part, we're gonna ask, well, if we do this, how fast is it going to spin in terms of RPM? So what is my RPM final? So when my I initial was, when my I was 20.8, we had an RPM of 60. And then when my I final is 8 instead of 20.8, what is the new RPM? So I can use conservation of angular momentum to solve this. Li equals LF. So L's don't change. I can expand L into I omega, initial, final. Okay. Now remember, here I have this in terms of omega, but I want it in terms of RPM. Remember, omega is 2 pi RPM over 60. So you can just replace this here. I initial 2 pi RPM over 60 initial equals I final 2 pi RPM final over 60. And then what you can do is you can cancel out the 2 pi's and you can cancel out the 60s, and you're going to be able to use this to solve for your final RPM. Okay, so let's just plug it in. RPM final is I initial, which was 20.8, times RPM initial, which is 60, divided by I final, which goes to the bottom over here, which is 8. So if you do this whole thing, you get 156 RPM. So your RPM is 156, okay? And that should make sense. You close your arms, you spin faster, okay? Your I is dropping by a factor of roughly 2.5. So your RPM, right, this is dropping. So your RPM is going to increase by a factor of roughly 2.5x. Okay, that's it for this one. This question, we had 4 steps, so I walked you through every single step. What you might see in a question like this is something much more straightforward, where I give you the setup and I just say, hey, if the RPM initial was 60, what is the RPM final? And then you're going to have to figure out that you have to calculate I initial, and then you have to calculate I final. Here I kind of held your hand through it, and I did it in multiple steps. But some questions you have to figure out. You have to do all of this stuff before you get to the final answer, and it may only ask you for the final answer, so you have to work your way there yourself. All right, so that's it for this one. Let me know if you have any questions, and let's keep going.